Okay, so what we're doing now in 3.4 is kind of the same thing we did in 3.3 with the first derivative. The first derivative, remember, told us whether the function was increasing or decreasing. It gave us the slopes of the graph at any given point. In this section, we're going to be looking at what's called concavity, which another word that we can use interchangeably would be the curvature, okay? The curvature of the graph, how fast it's curving. And then we're going to learn something called the second derivative test. So here's what we could say. The first derivative is to the slopes of, I better keep that, of f as f double prime is to the concavity of f. Now, that's an old way to do an analogy. They used to have them like that on the SAT test with the colon. This is to that, and the double colon means as, and then that is to that, right? So we're going to be doing everything we did in the previous section. We're going to be taking the second derivative now, seeing where it's undefined, setting it equal to 0, and making a number line chart and testing the sign of the second derivative. But that's not going to tell us where we have local max or mins. It's going to tell us where we have another type of point, which is called an inflection point, okay? So concavity is the curvature of the graph. So let's take a look at it. Example 1, let f be a function where the derivative is positive on some interval. Let's draw a picture of the 3 different ways on an interval we can draw the function f, knowing only that its derivative is positive. Well, if its derivative is positive on the interval, what do we know about the function? It's doing what? It's increasing. Okay, so the first way I might draw it, I'll just draw it out of the origin for simplicity. There would be one way to draw it, yes? And then in that case, you could say f is increasing at what rate? At a constant rate, good. All right, so notice we're not saying f is a constant. We're saying it's changing at a constant rate. So kind of like Mr. Crowley was asking in the quiz, we're talking now about how the slopes are changing. When you talk about it increasing, you're talking about the slopes, and then you're talking about how fast the slopes are changing. So over here, we could draw one now that increases like that. That's also increasing. But that one is increasing at a different rate. This one, f, is increasing at what rate? Yeah, increasing at an increasing rate. As you go further and further to the right, the slopes are still positive, but the slopes are getting steeper and steeper. And then over here, you can have it increasing like that. And in this case, if that's f, f is still increasing, but now f is increasing at a what rate? At a decreasing rate. All right, so how is the second derivative involved with this? Notice, first of all, if you look at this one, we would say this one has no curvature, okay, or no concavity. I don't think I have to convince you of that, right? It has no curvature. It's a straight line. Bless you. This one does have curvature now. The line is bendy. So we say that this one is concave up, okay? And you can kind of put a little mnemonic here, like a cup, okay? It rhymes, like a cup. A cup holds water. So you can imagine if there was another side to this, it would be like a cup holding water. And then this one we say is not convex. We say it's concave down, like a frown. Yeah, it rhymes. So this would be like the left side of a frown. All right, so again, we use concavity to refer to the curvature. Unlike in the science class where you have concave and convex, we're not going to use convex. We're going to talk about concave up like cup, concave down like frown. What we want to do is then see not how the y values are changing, but how the slopes are changing. So if you draw this, we could say that there's the slope of a tangent line, there's the slope of the tangent line, and there's the slope of a tangent line. They're the same everywhere, right? So here we could say that the slopes are constant. The slopes are constant. Over here, when it's increasing at an increasing rate, now we have some interesting things going on with the slopes. The slopes are still positive, but they're doing what? The slopes are increasing. Yep, the slopes are increasing. And over here, if we draw tangent lines at various places, again, the tangent lines are still positive, but now they're getting less steep. So in this case, the slopes are what? Decreasing. Okay. Well, if the first derivative tells us how the y values are changing, what derivative would I need now if I wanted to talk about how the slopes are changing? The second derivative, yes. F double prime tells us how f prime, which are the slopes of f, are changing. Anytime you take the derivative of a function, it tells you how the previous function is changing, which those are the slopes of f. Okay? Let's add this just like f prime tells us how f, which are the y values of f, are changing. Okay, so let's think about this. If the slopes are constant, what do you think the value of the second derivative is if there's no change? 0. The second derivative should be 0. Okay, because slopes being constant means there's no change. And the second derivative quantifies the change in the first derivative. Okay, cool. So if on any interval you know that the second derivative is 0, you know that the graph has no curvature. All right. Over here, if the slopes are increasing, then f prime is increasing. What can we say about its second, f double prime? Is greater than 0. It's positive, okay? And over here, if the slopes are decreasing, then the derivative of f prime, which again is f double prime, should be less than 0. Okay, so notice that if we now combine that information with first derivative information and function information, we can now not only know where the graph is at any given moment, that would be the function value, but we know if it's going up or going down, that would be the first derivative, and then we know how it's going up or down, that would be the second derivative. Okay, and then with a couple of points that we carefully select along the way, we can discern what the shape of any function is. Okay, so again, that's called the concavity, but curvature is interchangeable. Important idea. If f prime tells us how the y values of f are changing, then the derivative of f prime, or f double prime, tells us how the slopes are changing. So here's the relation between the second derivative and the concavity on an interval. For some continuous function again, if the second derivative is positive, we say that the function is concave up like a cup on that interval. So remember, the f double prime tells us about f. It tells us that it's concave up like a cup. But never forget that f prime also tells us something. F double prime also tells us something about f prime. It means that the slopes are increasing. Okay, very, very important. It tells us two things. It tells us that the function is concave up, and it tells us that the slopes f prime are increasing. If the second derivative is less than 0 on any given interval, then we say the function f is concave down like a frown. That tells us something about f, but again, it also means that the slopes are decreasing. And if the second derivative on any given interval is 0, then the function has 0 curvature or 0 concavity, which means the slopes of f are constant. Okay, so here's an easy way to remember the curvature of f, or the concavity of f, based upon f double prime. If the second derivative is positive, okay, draw a smiley face, but put plus signs in his eyes to represent positive, yes? Well, if you've ever seen anyone with plus signs in their eyes, I bet they've been smiling, right? It is hard to frown when you've got plus signs in your eyes, because you're happy, you're positive, you're upbeat, you're doing Rachel's challenge, all that good stuff, okay? So any part then of a smile, notice on our left, the left part of the smile is decreasing, right? And the right part is what I already showed you. It's increasing. So you can have decreasing concave up or increasing concave up. Anytime you have a second derivative that's positive, regardless of the first derivative, it's going to be concave up like a cup. And again, the like a cup not only rhymes, but it helps you remember that this holds water. So if we poured water into this smile, it would hold water like a cup. And then you can drink it out of his smile. Okay? That's kind of weird. But anyway, there's a plus sign. And yes, I made that meme. I went to like imageflip.com and I made my own meme. I'm pretty proud of myself, right? What? They're always dank. Yeah. Yeah. Okay, I made this one too. So everybody knows Walter, maybe, or no one knows Walter. Walter is the talking puppet for Jeff Dunham. One of them. Well, the puppet doesn't talk. I mean, the whole spiel is it's actually Jeff Dunham talking. But yeah. Anyway, Walter is kind of a grumpy old man, and if you notice, Walter, like many grumpy old men, they have little beady eyes, right? They're squinting. They're not happy. They're beady, right? They're like, ugh. And when you do that, they look like little negative signs. Okay. Now, if you look at someone and they have negative signs in their eyes, they're probably not going to be smiling. They're probably going to be doing a what? They're probably going to be a frowning, like Walter. Okay. So anytime the second derivative is negative on an interval, you get concave down like a frown. And yeah, that's a dank meme. Yeah, it goes without saying, right? Okay, now if the second derivative is 0 on an interval, then you have no concavity, 0 concavity, or, as I wrote, curve depravity, okay? So again, if you look at someone and they have zeros for eyeballs, right? They're probably in some kind of shock and they have a hockey puck smile, right? Ugh, right? They're filled with angst, so you get the straight line smile. So yes, you're welcome. You're welcome. All right, I thought of these entirely on my own, and you too can go to imageflip.com and create your own dank memes. Yeah, so you don't have to dank me for them. I understand that you appreciate them without danking me. Okay, ooh, was that a dank pun? Or do we not use dank in that context? Okay, all right, sweet. Okay, ultra dank. Okay. So there you go. Concave up like a cup, concave down like a frown, and 0 means no curvature. All right, putting it all together now. If we know the signs of f prime and f double prime on an interval, we know that the graph has to look like some of this. Now, again, if we know the f value, we know exactly where to put this on the coordinate plane. But we're just kind of looking in general. So let's look at this first piece here on the top left. If you take a circle and you just look at this piece right here, okay, that piece would be, let's go ahead and label it, increasing or decreasing? Okay, it's increasing, comma, concave up or concave down. So yeah, so I'm always going to abbreviate concave as CC, okay, and you could do that until the day of the AP exam. So increasing, concave down. So off to the left here, we know then the first derivative is what on that interval? Positive, and the second derivative is negative. Now it's an if and only if. So we're getting the information from the graph and filling in the inequalities on the first and second derivative, but it works the other way around. If you know the sign of the inequality on the first and second derivative, you know what it looks like. Okay, let's move over to this next piece on the right-hand side, this piece here. Okay, what do we know about that? Increasing or decreasing? That's decreasing. Concave up or down? Yeah, it's still CC down like a frown. Any part of a frown is concave down. Okay? So notice when it's concave down, the slopes are decreasing. How can the slopes be decreasing on the right-hand side? Well, they're going from a small negative to a bigger magnitude negative, right? So, yeah, that makes sense. So what do we know about the first derivative on that interval? Decreasing means first derivative is negative, and concave down means the second derivative is negative. Okay, let's look at this next little piece down here. That one right there. On that interval, the function's increasing or decreasing? Decreasing. Concave down or concave up? Concave up like a cup. So I say up like a cup, but I don't say any part of a cup. I usually say smile, right? Any part of a smile is concave up. So the first derivative is going to be what? Negative, and the second derivative is positive. All right? And then the last little interval here.
So even though the slopes are decreasing on
The slopes are actually increasing. Let's look at that. I was going to come back and do it after we finish this, but yes, you're right. It looks kind of weird, right? Because it looks like the slopes are increasing, right? It's becoming less steep. But steepness is a scalar quantity, right? So if you notice, the slopes are actually increasing because they're becoming less negative. This one might have a slope of like negative 30. This one might have a slope of like negative 10. This one might have a slope of like negative 1. All right, so the graph is getting less steep, but the slopes are still increasing. So great question. That was probably the appropriate time to ask. And now you can clearly see over here that the slopes are increasing because they're becoming more positive. So this interval is going to be increasing concave up like a cup. So the first and the second derivative are both positive. Okay. So now if you select a few ordered pairs, that is, you know some specific x and y values as coordinates, and you know what the sign of the first and second derivative are in between those points, you can then connect those dots with any one of these four types of arcs or straight lines if it has zero concavity, okay? Pretty darn cool. So knowing the actual function values, again, will allow us to place those on the coordinate plane. But first we need to then discover, okay, at what value of x can a function change its curvature, its concavity? And what types of values of x? All right, so here's the definition. An x value, call it x equals p then, that's in the domain of the function. So very much like a critical value, x equals c. Call an x value p is said to be an inflection value of f if the graph of f changes either from concave up to concave down at that point or from concave down to concave up at that point. That is, if f prime changes from positive to negative at x equals p, or f double prime changes from negative to positive. So that's what I said when we were grading the quiz. We don't want to say concave up to concave down. We always want to get in the habit of talking about a sign change. So this would be equivalent to like the first derivative test, right? When we talked about f prime changing signs from positive to negative. Now there is no local max, local min differentiation for second derivatives. We just call it an inflection value. So whether the second derivative changes from positive to negative or negative to positive, we just call it an inflection value. If you then come up with the inflection point, that would be the ordered pair. Okay, so what does the word inflect mean? If your voice inflects, what does it do? It changes. So you can remember that an inflection value is where something changes. What is that something? It's the curvature, also known as, the real name is concavity. When I think of concavity, I always think of like kids on Dia de los Muertos, like eating their Halloween candy in Mexico. And then the next day they go to the doctor like, oh, concavity. And the dentist like, siéntate, I will fix. Okay? I don't know why. I guess it's growing up in the valley. So, anyway, important note. A graph can also change its concavity at a discontinuity, just like a function can change its increasing, decreasing behavior at a discontinuity. All right? So that's important. You can have a vertical asymptote that's not in the domain, and it can be concave up on one side and concave down on the other side. Would you then call the x value of the vertical asymptote an inflection value? Let's call this x equals p, where the vertical asymptote is. The second derivative changes from positive to negative at x equals p. Is x equals p an inflection value? No, okay? Again, it's very similar to the definition of a critical value. It's just one rung higher. Just like the critical value, it has to be in the domain of the function. So again, a vertical asymptote would be what I would call a very important value, but it's not going to be an inflection value, okay? So if it's not in the domain, it cannot and will not be an inflection value. So here's an example. Inflection value, this goes from concave up to concave down, right? So the second derivative goes from positive to negative at x equals p. Here's another inflection value at x equals p. The second derivative goes from positive to negative. Notice that one kind of looks like a shark fin upside down, but that's a change in concavity. This one is also an inflection value, yes or no? Is it an inflection value? Well, let's see. The second derivative is it's concave up, so it's positive to the right. What is it on the left, on the right? Concave up or down? It's still concave up. So it's not an inflection value. And then the last one here, we'll just say, okay, it goes from concave down on the left, concave up on the right. I already showed you that. It's not an inflection value, though, because it's not in the domain. This one was not an inflection value because there was no sign change in the second derivative. Have a fantastic Thanksgiving. We'll see you back on Monday.